Chapter 8, Section 1. In this section, we're going to learn about what are called probability density functions. In today's world, data is gathered and analyzed in a wide variety of fields to help us understand and improve our society. The way this data is distributed throughout a population can be important to the people making important decisions about this particular field. This section will allow us to recognize the distributions in a population by representing the information using density functions. Density functions are also referred to as probability density functions or notated as PDFs. Let's understand and see what we're going to be looking at. So here we see a graph of U.S. employment age distribution in the year 2000. On the left-hand side, we have the fraction of the population employment per year of age, and then on the bottom, we have age in years. So we can find the percentage by multiplying the age by the fraction of the population employment per year of age. So for example, here we see this 9%. So 9% of the population that is employed is between the ages of 0 and 20. And again, we get that by multiplying 20, which is the length of this rectangle, times the height, which is just a little bit less than 0.5%. When we multiply those together, that gives us that 9% of the population is employed in these ages. Similarly, we can look at any other box. 60 to 80 will represent 15% of the population because, again, we have this width of 20. We're multiplying by something a little less than 1% to give us that 15% total. What's important to notice here is that if we add up all these populations, the 9%, 35%, 40%, 15%, and 1%, it'll equal 100% of the population. Now, when we write something as a percentage, remember we can write it as a decimal by moving the decimal place over to the left 2 places. So as decimals, these will all add up to 1. This is something that's really important with density functions. Density functions always add up all their data to 1. That's going to be important in a lot of the examples and calculations that we do. So let's look at some examples with this particular data. Okay, so if we want to estimate the percent of employed population between 0 and 40 years of age, how would we do that? Well, from 0 to 40, we have this 9%, which represents 0 to 20, and then from 20 to 40, we have this 35%. So we would add those together to get the total population employed between 0 and 40 years of age. So 9% plus 35% gives us a total of 44% of the population will be between the ages of 0 and 40. Now, what if we want to estimate the percent of employed population between 30 and 40? Now, this is a little more tricky because notice that 30 is not a cutoff point for one of these rectangles. Well, one of the assumptions that we make with probability density functions is that all the data is evenly distributed. What does that mean? That means that since 30 is right in the middle of 20 and 40, that 20 to 30 should be exactly half of the percentage that's in this block. So here, the total block is 35%, and so from 30 to 40 would be exactly half of 20 to 40, and half of 35 is 17.5%. So again, we assume that the population is distributed evenly through each group. Now, depending on the situation, this can create some inaccuracies. For instance, the graph showed that 9% of the population was between the ages of 0 and 20 were employed in 2000. Since we're assuming that the age groups are evenly distributed, we'd be saying that the people from this age group began working the moment they were born. Now, that's not very practical. We know for a fact that there are definitely more people in the upper age group working than the lower age group. To correct this, the data analyst would split the age groups into smaller segments. So instead of 10-year gaps, they might do 1-year gaps to get a more accurate representation of what the population was doing. So now that we've seen this represented graphically, which is how we'll usually do this, let's formalize the numerical portion of the population density by introducing the density function. So little p of x is a density function if the fraction of the population for which x is between a and b is equal to the area under the graph between A and B. That's the first part of a PDF. The second part is that if you integrate the entire PDF, so sometimes it's defined from 0 to 100, sometimes it's defined from 10 to 20, sometimes it's infinite on both sides, whatever the bounds are, if you take all the area under the curve, it should add up to 1, because again, that will represent 100% of the population. And our function should always be positive, so we should always be above the x-axis for all values of x. Now, while the general form of the density function is important and allows us to write a formalized version of our density graphs, we're not going to be using the equation to integrate our areas in this particular section. We'll see this again in 8.2, and we'll see how to incorporate this integral. For this particular section, we're going to be analyzing the data graphically, so we'll be looking at areas and visualizing estimates based on graphs. So let's see how this works. So, little p of x is a density function, given on the right here. We have this graph of p of x, and we want to find the value of a, which makes this a PDF, a probability density function. Now this is little a that we're looking for. So the most important thing to solve this type of problem is to remember that the area under the curve has to equal 1, all the area, which would represent 100% of the population. So here, our probability density function is defined from 0 to 20, so those are our bounds. So we know that the area under the curve equals 1. So that tells us that the area under A plus the area under B has to equal 1. Well, fortunately, these are nice rectangles. We know how to find areas of rectangles. We're going to do base times height. So the area of A, my base is from 0 to 10, so that's going to be my base, and then my height is 0.5a. So the area of A is 10 times 0.5a, which is 5a. Similarly, my area for B, again, my base is 10 units long because I'm going from 10 to 20, and then my height is going to be a. It goes up to a here. So I have 10 times a, which is 10a. Now I know if I add up all these pieces, a plus b, which is 5a plus 10a, that has to equal 1. So 5a plus 10a is 15a. If 15a equals 1, divide both sides by 15, and I get that my a has to be 1/15th. Because again, by a being 1/15th, that gives me that the total area under little p of x is 1, and that's what I need to solve this problem. Let's look at a triangular shape. These can be a little more tricky. There's two ways to solve them. So suppose that p of x is a density function, and we want to calculate the density between 10 and 20. So we're looking for the area under the curve from 10 to 20. So this gives us sort of an awkward shape that's not quite a rectangle or a triangle. But fortunately, we can split up this area into shapes we do know, into a triangle and a rectangle. Notice that's what we've done here in this bottom part. We've split it into two shapes that we recognize. Since we split the base of the original triangle in half, we can assume correctly that that will also bisect the height of this triangle by laws of triangles. So that means the height, where we hit at 10, will be 0.05, which is half of the original height of 0.1. So we want the area of A plus the area of B to give us the total area under the curve from 10 to 20. The area of A is going to be a triangle, so we're going to do 1/2 base times height. My base goes from 10 to 20, and my height is going to be the difference from 0.05 to 0.1. That's represented on the top here, and then we divide it in half, which gives us 0.25. Now, when we do the area of B, we're doing the area of a rectangle. So we do base times height. My base is 10 units long, the difference between 10 and 20, and my height is going to be 0.05. So 10 times 0.05 is 0.5. We add up the total area, we're going to add up A and B, to give us a total area of 0.75. So we found that the area under the curve from 10 to 20 of our PDF is 0.75. Now there's an alternate way to do this, because we can again use the fact that the area under the curve, the total curve, should equal 1. So if we label this third area C, if we know that the total area under the curve is 1, we can subtract off this area C, and what's left will be the area from 10 to 20. So here, area C, again, is going to be 1/2 base times height, because C is a triangle. My base is 10 units long. My height is 0.05, and I take half of that. So area C is 0.25. So if I do 1 minus this area, it just leaves me with the area of A and B. So I do 1 minus 0.25, and that gives me 0.75, same as before. So these two methods will give us the same answer. Sometimes it's easier to do one over the other, but again, you'll get the same result either way. So again, we found that the area under the curve from 10 to 20 is 0.75.